hello everyone. Luckily this is quite a short lesson. You might notice me talking a little bit faster than usual because, yeah, like I say, I've only got about 23% battery on my phone. It'll be totally fine. The one advantage of classroom teaching is that I don't literally run out of battery halfway through the lesson. Okay, we're doing Brownian motion today, which always kind of makes me smile because it just reminds me of poo. Like, it's got the word brown and motion in it, but it's not about poo. Before we learn about Brownian motion, we have to remind ourselves a little bit about particles. So have a little look at this sheet for me, please. If you've been to my Facebook group, you will have the worksheet. If you're not on Facebook, very soon I'm going to have a website that you can get this sheet from. But for the meantime, you'll just have to, do it in your head. You've got 5 pretty spherical objects here, and I just want you to match the spherical object to the word that you think describes it. So we've got something called hydrogen, and it's just a little pink ball with a plus sign in the middle, with a little green ball with a minus sign sort of whizzing around the outside of it. You've got a pollen grain, you've got a piece of soot, you've got oxygen, but it's actually 2 red balls smushed together, looks a bit like a bum. And then you've got water, which is 1 red particle with 2 white particles sort of smushed into it. And the red one's called oxygen and the 2 white ones called hydrogen. Which one of those, please, you can use each word as many times as you like, is a particle, an electron, an atom, a proton, and a molecule? And question number 2, because some of you are going to be pretty confident with this. Which of the above are microscopic? I'll give you 15 seconds and then I'll tell you. I'm hoping that most of you will know this already, but it's theory of science. We always like to catch up people who maybe haven't done any of this before. If you are just joining me live, this is the first activity. 5 seconds. Remember, you can use each word more than once. 4, 3, 2. Done it? Right, let's have a look then. Most of you will know this. This picture here with a little plus ball with a little negative ball whizzing around it. The negative ball is an electron and the positive ball is a proton. And those two things together, if there's an electron going around a proton, that's called an atom. And you get all different kinds of atoms. We did it in electricity. We'll do it again a lot when we get to radioactivity. This one is a hydrogen atom because it's only got 1 proton. If it's got 2 protons, then it's a helium atom. If it's got 3 protons, it's a lithium atom. And you might have heard of the periodic table. This is a list of all the atoms that humans have ever discovered. For today, we don't have to think about electrons and protons, so we're just going to think of atoms as being little balls. So when I just show you a circle that says hydrogen in it, you know that's an atom. It has got an electron and a proton in there, but we're not going to bother about that. Okay, good. So that's what an electron is, that tiny little negatively charged thing. That's what a proton is, and that whole thing is an atom. These things then, these oxygen balls smushed together, well, given what I just told you, you might be thinking, oh yeah, well that's an oxygen atom, and that other side of the bum, that's an oxygen atom, those 2 are hydrogen atoms, that's an oxygen atom. That is true, but particles made of more than 1 atom, it's like more than 1 atom bonded together, that you call that a molecule. So in fact, this is an oxygen molecule, even though it's the same kind of atom bonded together. That's an oxygen molecule because it's got 2 oxygen particles, atoms in it. And this would be a water molecule. Actually, you know, H2O, 2 hydrogens, 1 oxygen makes a water molecule. Right. So air, did you know this, is made of molecules, mainly pairs of oxygen atoms and nitrogen atoms. So you'd call that an oxygen molecule and a nitrogen molecule. For roughly, on average, obviously, for every 100 air particles, there are about 78 nitrogen molecules, 21 oxygen molecules, and you know what the 100th particle would be? 1 argon atom. Ugh. Well, but forget about that guy, okay? If you need to say anything, if you need to talk about air in your exam, say air molecule, right? Good. So, what have we got? We've got that's an oxygen molecule, that's a water molecule, and hopefully you will be fairly okay with the fact that they're all particles. You could say that they're all particles. I'm always calling them all particles because obviously you're all in different places and I don't want to get too technical where I don't have to. So you can say particle of water, carbon dioxide particle, an electron or a proton would be a particle. But we need to be a little bit more specific when we're talking about Brownian motion. So which of those are microscopic? Well, microscopic means something can only be seen with a microscope. So a pollen grain is microscopic. I mean, you see lots of pollen together, but actually one pollen grain, you can't really, unless it's a really massive one, you can't see it with your eyes, but you can see it through a microscope. Look at this. This is a Dartmouth electron microscope facility at Dartmouth College, and Wikipedia have brought you this beautiful picture of some pollen grains. So this is the pollen from a sunflower. That's the small spiky pink ones here. Morning glory, nice plant. That's the big mint green ones here. The lily pollen, is a bean-shaped dark green one, and a castor bean is the little light green ones. So this is what those pollen grains look like if they were like 500 times bigger than they are. The colours are made up. I'm sorry, I can hear you asking. The colours are made up. It's still incredible though, isn't it? Look at that. That's an actual piece of pollen. So pollen is microscopic. You can see it through a microscope, you know, like Dartmouth College is showing us here. You couldn't see it with your eyes. Pieces of soot are also microscopic. You can see those with a microscope. Hydrogen and oxygen and water. No, they are not. You cannot see those through a microscope. There are at least billions of atoms and molecules in one grain of pollen. You cannot see them with a microscope. This is very important. So now we have to talk about this guy, Robert Brown. He was probably a real happy-go-lucky chap. It's not a great photo. Robert Brown, botanist, like biologist, studied plants and stuff in the early 1800s. He looked at some pollen grains which were suspended. You okay with that word? Suspended in water. So here is the water. It's green. I don't know why. So pollen grains, they weren't like floating in the top, they were suspended, right? And he noticed something really weird. He noticed that they were moving in a kind of zigzaggy motion. So, for example, here's one pollen grain. It would have been doing this. Completely random. It was moving in a zigzaggy, random pattern. Here is a better diagram. There you go. So this is a pollen grain, this red thing here. And these are the blue things. This is the water. But obviously you can't see the water. So it just looked like this pollen grain was zigzagging on its own. And he called this motion, or this motion became called Brownian motion. I really wish it wasn't, because Brownian motion, like 5 syllables, is too many syllables. It makes it sound too complicated when it's just a thing that can be seen zigzagging around in a thing that can't be seen. And it also sounds like poo because of brown and motion. But yeah, what was happening was that obviously the water particles couldn't be seen through the microscope. They were invisible. The pollen grain could be seen. So what's actually happening is the invisible water particles are bashing into the pollen grain, which can be seen, and making it move around. But we didn't know that at the time. We didn't have a clue. In the early 1900s, and certainly the 1800s, people didn't know that atoms existed. Right, so question for you then, because I've done a lot of talking. Based on what I've just told you about particles, can you describe this red thing and these blue things, please? Just like write what they are. What are the red thing? What's this red thing, and what are these blue things? You might want to use 1 word, 2 words. You might want to use 3 words. Be as precise as you can. What's the red thing? What's the blue thing? Actually write it down, please. Imagine it's an IGCSE answer. You got it? The most precise description based on just all the words that we've been talking about for particles. So what I've said, well, I've written the question, that would have been useful for you to see. What's the blue, what's the red? I've said that the little blue things are water molecules, right? Water molecules, H2O, 3 atoms bonded together. And the red thing I've called a microscopic pollen particle. Let's be really clear and precise about this in case we ever do this at GCSE. The pollen particle is microscopic, which we're used to just meaning really, really small, but actually in this situation it means you can see it with a microscope. The water molecules are not microscopic. They are, in this situation, if you were looking at this through a microscope, they would be invisible. Is that okay? So it looks like the pollen's moving around on its own. So it's actually not. It was the second most famous scientist on the planet who realised what this motion meant. I mean, obviously, it's just an opinion. It's not a fact. Who do you think I mean when I say the second most famous scientist on the planet? Everyone on Facebook said the other one. You got a name in your head? I was thinking Einstein, because Newton's the most famous. Everyone was saying Newton, maybe Einstein's the most famous. I don't know. Anyway, but Einstein wrote a very famous paper about this Brownian motion in 1905, because like I say, at the time, a lot of scientists didn't agree that atoms even existed. Einstein and many others did more experiments and eventually proved that all stuff, like matter, just means stuff, is made of tiny particles that are constantly moving about. And this is called the kinetic theory of matter. Again, just like such a terrifying phrase for such a kind of beautiful, simple fact. The kinetic theory of matter. So we've looked at how kinetic basically kind of means movement, like movement, energy, kinetic. Matter means stuff. So the kinetic theory of matter is this theory that stuff is made of particles, and those particles are always moving around. If it's a solid, like my whiteboard or my hand, the particles are just kind of vibrating on the spot. But if it's a fluid, a liquid or a gas, they're both fluids, then those particles could be moving around with quite a lot of energy. Let's do our very simple activity. I said to bring a bowl of hot water and a bowl of cold water and some food colouring. I'm using brown because Brownian motion, yeah? So don't move the bowls. I should have said that at the start. But do not move the bowls. Get a little bit of food colouring on the end of a teaspoon, or just drop it in if you're using the liquid stuff. Put it in the cold water, see what you see, and then put it in the hot water, see what you see. What are you expecting to see? That's important. We should think about that. I'm going to blob this food colouring into the cold water. What are you expecting to see? Let's do it. Some food colouring has come off the spoon and gone into the water. Ooh, is that what you're expecting? And it's spread out a bit. It's formed a circle on the bottom. We've got a beautiful kind of spiral shape. That's nice. I should be reading my fortune in that. And now I'll do it in the hot water. What are you expecting to see? The same? Different? Yes, I think probably a lot of you are going to be fairly comfortable with this. Whoa, it's really splodging out. Look, it's spreading. It's spreading so far. So there's a really noticeable difference between the hot water and the cold water. The hot water food colouring is spreading out a lot further than the cold. And this is because of the fact that the particles are moving. That we've talked about this a lot before, you know, the warmer part, when you heat stuff up, liquids or gases, the particles start to vibrate more, start to move around more. So the particles in the hot water are moving around a lot more. So they're colliding with the food colouring a lot more, so causing it to spread out. What you're seeing here is not actually Brownian motion. This is something called diffusion, but it's caused because of Brownian motion. Brownian motion is the thing that's microscopic being collided with and bashed around by the thing that is invisible, right? Like it could be a piece of soot in air, so the soot is microscopic and the air is invisible, or it could be the pollen in the water. Those are the two famous cases. So obviously this food colouring, this is not Brownian motion that we're seeing because the food colouring is not, it's not microscopic. It's not like, yeah, it's not the individual ziggy-zaggy pathways that we're seeing, but it's caused by Brownian motion. Right, I'm quite pleased with this. You can really let yourselves go here, see how many you can find. I've got a paragraph written by a very enthusiastic student of physics, but they've made some mistakes. So if you've got the worksheet, I've put it on a whole page because I want you to cross bits out and improve bits, okay? How many mistakes can you find? Can you correct them? You can put a few ticks next to the things that you're happy with if you want to make it a bit more positive as well. Here we go. I've put, if you've got the sheet, you can underline all the mistakes you can find in this paragraph and have a go at correcting them in the margins. Robert Brownian studied particles of pollen in water. Robert Brownian studied particles of pollen in water. He noticed they moved in random zigzag patterns. Sometimes they moved in curved paths. It turns out this motion is caused by microscopic water atoms colliding with the pollen. What Robert saw proved once and for all that the particles in fluids move quickly and randomly. We've still got 16% battery, loads of time. So I'm going to give you almost a full minute for that. All right, let's do this then. It's Robert Brown, innit? It's not Robert Brownian. Studied particles of pollen in water. I'm okay with that. They are particles, aren't they? You could add something here. You could say microscopic particles. That would be even better. Robert Brown studied microscopic particles of pollen in water. He noticed they moved in random zigzag patterns. I don't really love the word pattern here, actually, because that suggests that there's some sort of method, doesn't it? And that I suppose it's not really, if it's random, is it still a pattern? I don't know. It's totally random. Sometimes they moved in curved path. No, they don't do that because it's caused by collisions. So it wouldn't move in a curved path. That's if you throw a ball, it doesn't suddenly start to curve unless there's another force acting on it. It turns out this motion is caused by, well, what's happening here? Microscopic water atoms. No, they're not atoms, are they? And they're not microscopic because you can't see them with a microscope. So water molecules. Robert Brown studied microscopic particles of pollen in water. He noticed they moved in random zigzag patterns, random zigzags. It turns out this motion is caused by water molecules colliding with the pollen. What Robert saw did not prove, actually, once and for all, that the particles in fluids move quickly and randomly, but it certainly helped to prove that. It was Einstein and various other scientists who went on to do more experiments to show that particles in fluids move quickly and randomly. Phew, right. Did you get all that? So that's Brownian motion. I did say that we'd do thermal expansion this lesson, but I'm going to put it off ever so slightly, actually, because this lesson kind of leads nicely into that lesson. Right, you got some, well, it's not homework, because that makes it sound like you had to do it, but I gave you some questions last week that I said if you wanted to have a go at, then we would mark them this week. So I've made this lesson a little bit shorter so that we've got time to do that. I gave you these pictures of my niece and my husband's feet because we were doing about pressure last week. So I said to just assume that the feet are rectangles, right? If my niece has got a mass of 12 kilograms and my husband's got a mass of 75 kilograms and my niece's foot is 0.11 meters by 0.05 meters, and my husband's foot is 0.3 meters by 0.12 meters. Which one of them will cause the most pain if they step on my foot? Which one of them is putting the most pressure on my foot? So we'll mark that in a sec. before I do that, I want to tell you how you can support me, because you totally can. If you are enjoying these IGCSE lessons, they are totally free, but I would very much appreciate a contribution, because that is the only way that I get paid, basically. So if you want to go to my About section on YouTube and sign up to support me, find the link that says it's to Coffee, or Ko-Fi, as maybe I should be calling it. Find the link that says Theatre of Science Coffee, click on it, send me a few pounds a month. It's hopefully not that much from you for like various lessons, and it's enough from everyone that it's a living for me. And only if you're watching live, this works. Sorry, if you're watching on, it works if you're watching on catch up before Christmas 2023. Last year I brought out a Christmas magazine that I was really pleased with, but obviously some of you don't have it. It's like a couple of hundred of you who don't have it because you signed up to support me after Christmas. So I'm going to put it in my coffee shop as pay as you feel. So I haven't quite worked out. I'm going to have to make it that you pay me minimum how much it costs me to post it and how much it costs me to print it. But after that, I'm just going to make it pay as you feel. So if you feel like you support me loads anyway, you can just have it for cost price. And if you feel like you want to give me a Christmas tip, you can totally do that as well. I love it. It's got a comic about the Christmas truce in it that happened during World War I. I researched so much about the Christmas truce, so it's all the details. It's got a Christmas tree spotting guide in it that's like a pull out and keep, so you can tell like what kind of genus, what type of Christmas tree you've got if you found a Christmas tree. It's got a very cool activity you can do with the pine cone. Yeah, it's just got all kinds of pine tree related stuff in it, and I'm very proud of it. It's got some pine tree bunting you can make. I'll send you some string, and then it's got details about the different trees on the bunting. But yeah, it's not up there yet. Great ad for something that doesn't exist yet. After this, I will put it in my coffee shop. Just pay as you feel. Yeah. So if you do support me already and you'd like some Christmas science mag in your life, then you can. Right. This question then. I'm just going to use, should I say hello to people first? Yeah, I've still got 13%. I'll just go over to Facebook and say hello to people. If you're watching on catch up, sorry, you'll just have to skim forward, won't you? Maybe not that many people have said hello. Then we can crack on with the question. Who will be watching this? Let's see. Henry! Hiya, Henry. All right, Henry, we'll just get on with the answer then. Brownian motion with a random motion of particles suspended in a fluid resulting from the collision with fast moving atoms. Did you write that yourself? If you wrote that yourself, that's brilliant. If you didn't, then you found a description. That's good too. That's excellent. Right, a quick bit of revision then, because I think it's quite useful that we research. 2 comments now. Who's that? I think it's quite useful that we do a little bit of revision on things that we've done previously. Oh, Luke's here as well! And me! Shouts Luke. All right, well, maybe you two know this already, but we'll do this as well for people who are watching on catch up. I am going to get some more 10s for Christmas. I'll treat myself. Wow. Just wow. So bad. Wow. There's just no point, is there? There's no point. Let's talk about the difference between mass and weight. Do you know this already? So mass is measured in kilograms. Mass is, a good description of mass is, it's sort of how much stuff is in a thing. So a 1 kilogram bag of sugar, that 1 kilogram is its mass, and that sort of tells you how much stuff is in it, right? So if a 1 kilogram bag of sugar is on Earth or on the moon or near Jupiter, its mass doesn't change. It's still got that many particles in it. Weight is a force which is measured in newtons. Weight is a force. Force is measured in newtons and newtons. And your weight is how much you are being pulled sort of downwards, if you like. It's how much gravity is pulling down on you. So weight changes depending on where you are. If you are on Earth, then Earth is pulling on you with a force of 9.8 newtons per kilogram. So for every 1 kilogram that is on Earth, it's getting pulled on with a force of 1.8 newtons, right? Whereas if you're on the moon, here's the moon, then you would only be pulled on with a force of 1.6 newtons per kilogram. We call this number 9.8 or 1.6. We call it little g, which means like sort of well, you could call it acceleration due to gravity, or you could think of it as just how much gravity is pulling on you. So on the moon and on Earth, G is different. So your weight is different. Weight is equal to, I'm going fast because this is revision, right? Weight is equal to this little G number times mass. Phew, we got there, right. So if we use the last 10% of my battery to come back to the PowerPoint here. Here we go. We want to work out the pressure that's just on Earth that my niece and my husband put on my feet if they stand on it, right? So pressure, we learned last week, is force divided by area in meters squared. So first of all, we need the area. The force pushing down would be their weight. So we need the area of their feet and we need the weight, right? So the area of my daughter's foot is, remember to use the meters because we're getting our result in pascals, and that is measured, has meters kind of in it, newtons per meter squared. So it's 0.11 meters times 0.05 meters, which gives me an area on my niece's foot of 0.0055 meters squared. Right. Phew, so well done if you got that. Let's get rid of all this. Let's work out how much my niece weighs, shall we? So my niece's mass is 12 kilograms. We're going to times that by 9.8 to get her weight. 9.8 to get her weight. And you should have got my niece weighs 117.6 newtons. So it's force divided by area for the pressure. So 117.6 newtons divided by the area of her foot. She's only stepping on me with one foot, so it's 0.0055 meters squared. Gives you an answer of 0.0055. 21,381. Phew. And that's pascals, right? You could write newtons per meter squared. Newtons per meter squared is what a pascal is, but write pascals at the end. So let's do the same thing for my husband then. So he weighs 75 kilograms. So we've got to find his weight, and he's on Earth, so we'll times that by 9.8 newtons per kilogram as well. And then, so if that's his weight, let's just do it all together. We're going to divide that by the area of his foot, which I've already worked out. It's this, we'll just pretend their feet are rectangles. So the area of his foot is 0.3 meters times 0.12 meters, which is 0.036 meters squared. So let's stick that in our equation. 0.036 meters squared. So this is my niece. How do you spell niece? Is it E? That's not it, is it? Is it I-E? I before, no, it is E. Anyway, sorry, this is not really part of the lesson. That's my husband's pressure, isn't it? His force, his weight divided by his area, which is 75 times 9.8 equals divided by 0.036. 20,000, oh, gasp, what a surprise. It's almost like I did it on purpose. 20,416.7 pascals. So, oops, it froze. It froze because I've only got 10% battery left. Sorry, have I just done all this work without you? The answer was, the pressure that my husband puts on my foot is 20,416.7 pascals. And the pressure that my niece puts on my foot is 21,381 pascals. So in fact, even though my niece's mass is much, much smaller, because her feet are also smaller surface area, it's my niece who is putting more pressure on my foot and therefore would potentially hurt me more if she stepped on my foot. Weird, isn't it? Right, and then I don't know why I did this. I then said, what if my husband was on the moon? Imagine he's wearing a spacesuit that weighs 50 kilograms. How much pressure would he put on the moon's surface? Deep regret for this question, but here we go. I don't know why I didn't think that the spacesuit would increase the surface area of his foot. Obviously it would, but here we are. How much pressure would my husband apply to the ground if he walked on the moon? Assume a spacesuit weighs 50 kilograms. So his new mass is going to be 75 kilograms, his old mass, plus 50 kilograms, which is 125 kilograms. He's on the moon. So his weight is going to be his mass times little g on the moon, which is 1.6 newtons per kilogram. So, right there, I've put it. So his new weight on the moon is only 200 newtons, much less than before. So he obviously still got the same area of foot because of my weird situation where he's wearing a spacesuit but also still is trainers. So if you divide his new weight by the same area, you get 5,555.6 pascals. So he actually is putting far, far less pressure on the surface of the moon, even though his mass is a bit higher. Whew. Hope that helped. Ha 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 ha. We all had fun, didn't we? It's nice getting the right answer, and it's incredibly useful to get the wrong answer and then working out why it was wrong. Okay, I'm going to go back to my Facebook comments to see how hard Luke and Henry are complaining about that, if they're even still here. They might not be here. I bet they are. They're always here. Let's see. Whoa, more comments. Luke! Punch the sky! All your answers were right. Wow, that's brilliant. Well done. Weight is a force. Also, it's niece. Oh, it is with an I. Oh, thanks. This is why I have Facebook comments in it. Should I correct? Yeah. I might do some English lessons next year, so getting my practice in. Hello, Luke. Oh, it's just you. Excellent. Loving the comments from you guys. Thank you very much. Has cheered me up immensely. Okay, I'm gonna go. I was saying we've got 2 more IGCSE lessons before Christmas. I don't think we're not going to finish off the module or anything. We'll have to pick up again next year. 2 more IGCSE lessons. 2 more all ages lessons that we're doing on flight at the moment if you're watching live, and I think 1 more Lego Storytime show because I do have to do some parenting next week because my children's school breaks up a little bit earlier than I thought it did. It's fine, but yeah, I think next week's Lego Storytime show will be on reindeers because we haven't done them yet, and they're Christmassy, or are they? I'll research them and tell you. Right, I'm gonna go. Thank you so much for coming, you lot. I'll see you very soon. Bye.